Hello, some of my favorite Algebra 2 students. Honors Algebra 2, I should say. Honors Algebra 2. That could make a lot of people upset. I believe this is your homework. If not, then I don't know where it is. But I'm just going to do a couple problems from each section, and hopefully that will help you out, I guess. So, write each equation logarithmic. You have to remember that there's a base for exponential and there's a base for logs, and they're just like the same thing. So for this question number 4, my base here is 10. So this will be log base 10. And you're basically flip-flopping the actual numbers. It's whatever it's equal to is what you take the number, and whatever your exponent is what it's equal to. So this base right here stays the exact same. This is exponential base, this is a log base. Evaluate. One thing you can do here, you could rewrite it so that it would be as exponential if you want to. It might be more helpful. Like this is, let's say, equal to x. So I'm doing question 6. So I can rewrite this as 4, because this is my base right here, raised to the power of x is equal to 8. Now this doesn't really help me, but what you want to do once you do this is rewrite it so that they have the same base. I can rewrite 4 as 2 squared. So that's 2 squared, the x power. I can rewrite 8 as 2 cubed. I'm just going to move over here. So power to power, you have to remember that you multiply. So this is actually 2 to the 2x is equal to 2 cubed. Once that happens, once you have your bases, your exponential bases are the exact same, they cancel out. Or if you did log base 2 on both sides, they would cancel out. So really you're putting your exponents equal to each other because your bases are the same. So they have to have the same exponents. So if I divide by 3, just kidding. So if I divide by 2, so x is equal to 3/2. So you want to rewrite it and then try to get the same base if you're going to do this longhand. Otherwise, you can do it on your calculator, and the nicer, newer calculators, there's actually a button where you can change the base of the log. If you don't know where that is, you should let me know. Okay, when we are graphing, it's the same exact transformations that you had for any function. Any function inside the equation moves left and right, always opposite. Outside the equation moves up and down. So, just a little couple things. This is log base 5. This is log base 3, log base 7, log base 4. There's nothing inside here. It's on parentheses. This is inside, inside, inside. This is outside, outside, outside. So let's just do this one. Or actually, let's do this one. So this is on the inside. Inside is always opposite. So this is actually going to move right 5. This is on the outside. So it moves up 3. Inside, left, right. Inside, opposite. Outside, as is. Write each one as exponential. So again, your base here is the same type of exponential base. That's my base. So it's 2. And it's almost like flip-flopping these. 2 raised to the 7th is equal to 128. Or 7 raised to the 5th is equal to 16,807. Find your domain and range. So before we talk about domain and range, we have to talk about what the graph looks like. So domain, when you're graphing a logarithmic equation, you will never get x to equal 1. You're never going, or 0. Sorry, you're never going to get x to equal 0. So that's a domain restriction. So in my parent function, so this is kind of like a parent function because there's no adding, subtracting. You can think of it as same thing, 5 raised to the y is equal to x. So let's say if I put 1 in for y, that would be 5 to the first would be equal to 5, so it would be 5, 1. It's kind of like flip-flopping it. Or again, you can fill this out in your calculator. You can put it into your y equals and go to your table too. That's really the best and easiest one to do. And let's say if I put -1 in for y, that's the same thing as 1/5. So rough sketch this. So 5, 1, 2, 3, 4, 5, 1, about right here. Again, depending on what your base is, it's going to be a little bit different. And -1, or 1/5, and -1. So like really close, but not really there. You're going to have a shape that looks like this. You're never, ever, ever, in your parent functions, you're never, ever, ever going to pass this line. You're not going to ever get 0 out, because x will never be equal to 0. Because if you plug 0 in for y, if you go back to this equation and plug 0 in for y, you would get 5 to the 0 power, that's equal to 1. Okay, so if you plug 0 in for y, it'd be 1. That means 1, 0. 1, 0, I didn't draw this the best, but 1, 0 should always be on your graph. 1, 0. This is a better graph. So my domain is always, okay, what numbers can x be? And depending on how your teacher does this, it might be different. So if they don't do domain and range written like this, then let me know when I can change it. But it's never going to be 0, but it can be really, really close. So in this case, it's all moving to the right. Moving to the right, that means x is getting larger. So x is greater than 0. It is not equal to. It will never pass through 0. My range, if you look here, if I'm going down forever and ever and ever, here I'm going up. It's going to get small, but if I put in like a bajillion, it's going to get up there. So in this case, it's going to be all real numbers, or -infinity to infinity, or just write out all real numbers. So let's say if we had a problem like this, and one right here. This is only going to change because it's on the inside. X is moving to the left 2. The stretch here, this is a stretch, this 2 is a stretch. It's not going to do much to your domain and range. And right here I'm just talking about the domain and range. But the left 2 is going to change my domain. So now x is going to be greater than -2 because I moved left 2. In your parent function, it's always going to be 0. And yes, range, again, it will still be all real numbers. And I don't know how your teacher likes to do that. Actual graphing. So again, I'm not sure how your teacher exactly likes to do this, but how I would typically do this is make a table and then graph the points. So now I'm not going to use this section, but what I'm going to do here, x, y, I'm going to rewrite this as 2 to the y is equal to x. So I'm going to actually find my y values and plug them in. So I'm going to pick, let's do -2, -1. I don't know how many points your teacher likes to do, so it could be different. But if you put -2 into your equation, that'd be 1/4. Put -1, it'd be 1/2. Put 0 in, 2 to the 0 power is 1. If you put 1 in, 2 to the first power is 2. Put 2 in, you get 4. So I plot all those points. So these are the points plotted. Make me a little curve. Should never, ever, ever, ever pass through the arrows, kind of bad, through the y-axis. Again, there's a horizontal asymptote here. It's never going to pass that. So now if I look at a zoom in, just trying to do my points better. It also says, find the domain and range. My domain would be x has to be greater than 0. Or you could say parentheses 0 infinity. And again, I don't know how your teacher represents it. Range, all real numbers. If you haven't noticed, range is going to be all real numbers majority of the time. I'll do one more of these because of the asymptote. So next one, whoopsie daisy. Next one right here. This is going to move it left 3. So what you want to do here is think first, what's the equation? So it's going to be 4 raised to the y is equal to x plus 3. But it would be actually better if you did 4 raised to the y minus 3 is equal to x. So same type of thing. Still going to use my x, y, so I'm going to make my table. X, y. Since this is moving left 3, I'm going to pick the same numbers as the y as I did before. -2, -1, 0, 1, 2. Plug it in. So if I plug -2 into my equation, that's going to give me 1/16. Subtract 3, give me about 2 15/16. Negative. Plug -1 into the equation, it's 4 raised to the -1 is 1/4. 1/4 minus 3 is -2 3/4. Plug 0 into your equation, 4 raised to 0 power is 1, minus 3 is -2. Plug 1 in, 4 to the first is 4, minus 3 is 1, and 2. 4 squared is 16, minus 3 is 13. So plot those points. So those are my points. If I want to, I could draw on this horizontal asymptote. And if I draw my graph, that's my dot in the background. It's going to look something like that. So my domain, x is greater than -3. It can't be -3 because I moved to left 3. And range is all real numbers. And finding the inverse. So, I know, let's do 29. So inverse is you switch your x and y. So x is equal to log y minus 6. And you have to solve. So my base here is 10. If there's no number, it's base 10. So I can rewrite this as 10 raised to the x is equal to y minus 6. And then add my 6. So, oopsies. 10 raised to the x plus 6. No, honey, I can't. Is equal to y. So you flip-flop your x and y, rewrite it as exponential, and then solve from there. So again, if I would have done, I know, that one's easy. These other ones are easy. You guys are so smart. These are easy. X is equal to log base 2 of 4y. Again, rewrite it as 2 to the x is equal to 4y, and then divide by 4. So your inverse function would be 2x over 4. So just go over question 32 quickly. You can look for the illness today for that one.
Hi, Mom.
Hi, sweet pea. So looking at question number 2, if you were to rewrite this, this would be your base b raised to the y is equal to x. It's asking why can this right here not be 1? Well, if you think about 1 raised to any number that it so wishes to be is always going to be 1. So you're not going to have a graph. If you had a graph, it would be, here's my graph, here's where x is 1, here's where y is 1, and you can't do that. You're not going to be able to have your x and y both be 1 all the time. It would just be a point on the graph, and that's it. So you cannot have that because 1 raised to any number will always be equal to 1. There you go. Hope that helps. If it doesn't, sorry. If it does, woohoo, you were smart. You can figure it out. I'm always here for help if you need it. Sorry this was so long. All right, bye-bye.